Okay, this is video number 2 for section 5.1. So the first one that you should have watched would have been the Mrs. Myers video. So this is your note packet. Quick review. I do want you to do this, and remember when you're answering these questions, try to think about area. So what this section is all about, and if you haven't watched Mrs. Myers' videos, I'd like you to watch that one first. So she goes through a couple examples. I'm going to go through it in a little bit more detail. But what the objective is here is the integral or the antiderivative is what we're getting at. And if you remember in chapter 1, well, the pre-chapter 1, that pre-chapter that we did, where we briefly went over the purpose of limits, derivatives, and integrals. Well, integrals were what we used to estimate the area under a curve. So this is just a curve I drew, and what the integral or the antiderivative does is it helps you, derivative, helps you estimate what that area is. So when you have a curve, you can't really find the area. So Mrs. Myers went over this. So investigations involved with instantaneous rate of change led to investigations of slopes of tangent lines. So that was all your derivative stuff, right? Slopes of tangent lines. Investigations involving area under the curve led to a second branch of calculus, integral calculus. And remember, you can think of an integral as an antiderivative. We get to that more in the second part of this chapter. In 5.1, you will learn about estimating with finite sum sets, which sets the foundation for understanding integral calculus. So this is kind of like you got to learn to do it the hard way first. Kind of like when we learn derivative, we learn definition of the derivative first. This estimating methods that we're going to use in here is what you have to learn before you learn how to find the area using the integral. So the area problem, definite integral. Tangent lines / rate of change problems are derivative. So there's there's 3 major topics we studied: limits, derivatives, integrals. We're starting the third. The area problem will give us one interpretation of a definite integral. Definite means you have an upper and lower bound, kind of like a starting point and an ending point for your area. And it will lead us to the definition of a definite integral. First, assume that you've got a function f of x that is positive on some interval. So that's what this graph is showing you. What we want to do is determine the area of the region between the function and the x-axis. So we're always talking about area under the function and the x-axis. So here's the function. It's the x squared, the one that she did in her video, but it's shifted up 1. And the region is from 0 to 2. In other words, we want to determine the area of the shaded region. I have nice color shading. We can't determine the area exactly, however, we can do an estimate. So the first thing we need to find out is about these subintervals. So these are the rectangles that we're going to divide this region up into. So this estimating method that we're learning, called Riemann sums, we're always taking the area and we're dividing it into rectangles. So it says we will divide it into n subintervals. So as we do some more of these problems, it will tell you divide it into 5 subintervals or 4 subintervals, something like that. So the way you find out, this is how wide your rectangles are. The way you find out how wide your rectangles will be is you take b minus a. So let's say, for example, they asked us to divide it into, I'm going to say 4 rectangles, or 4 subintervals. So the width of my rectangles in that case would be b minus a, which would be 2 minus 1, because I'm on this interval from 0 to 2, which is from a to b. So I'm going to say 2 minus 0 divided by 4. So that's 1/2. So that means the width of my rectangles would be 1/2. So I'd have one rectangle here, one here, one here, one here. All right, so let's keep going with this example. So here is a visualization of the different approximation methods we would be using. So the function value at the right endpoint, so this would be what she referred to in her video as the RAM. So that's the right endpoint of each interval will determine the height of the rectangle. Choosing the right endpoint for the rectangle will overestimate the area because f of x is increasing. Okay, and I guess my guess was pretty good because we are doing 4 rectangles. And the width, remember the width is your delta x, and that's going to be 1/2. So pretend these rectangles weren't here and you had to draw them. So you're going to do 4 rectangles and they're going to be width of 1/2. So you'd have a rectangle. That's how you would start, saying I have 4 of them. And then for the right endpoint, you'd say, well, this is the base of my first rectangle. I'm going to go to the right side, go up until I hit the curve, and that is how I'm going to set the height of my first rectangle. So there's your first rectangle. My second rectangle, the bottom of it is right here. I go to the right side, I go up until I hit the function, and that's where I set the height of my second rectangle. And then on for third and fourth. So the area is adding up the area of each of these rectangles. So that would just be base times height. So they're all going to have a base of 1/2. So you'll notice this 1/2, 1/2 is all the way through here. And this f of 1/2 is saying when x is 1/2, what is y equal to? So this point right here would be when I put 1/2 into my function. What was my function again? X squared plus 1. So it would be 1/2 squared plus 1. So that would be the height of that first rectangle. The height of the second one would come from this point. So this point is when I plug 1 into the function. So this y value would be 1 squared plus 1. Remember, I'm just substituting these x values into my function. So they're writing it here as base times height, base times height. This is what happens when I plug 1/2 into the function. I get 5/4. This is what happens when I plug 1 into the function. This is what happens when I plug 1.5 into the function. And this is what I get when I plug 2 into the function. So there's my area estimate. So that would be what you would call your RAM. Okay, now this one is left endpoints. So this is LRAM. So you still have 4 rectangles, same thing, the base is 1/2 on all of them. But on this one, if this is my rectangle, I go to the left side, I go up till I hit the function, and that sets the height of my rectangle. So that's the height of my first rectangle. Here's the base of my second rectangle. Because I'm doing LRAM, I go to the left side, and I go up till I hit my function. That sets the height of my triangle. And so on. Rectangle. Here's my third rectangle. Go to the left side of it, go up till you hit the function. That sets the height of my rectangle. So area is still, the base of all these triangles is 1/2. So you see this 1/2, 1/2, 1/2, 1/2. So this is base, and this is height. So this is the 4 rectangles. 1, 2, 3, 4. Base times height, base times height, base times height. So the first time I plug in 1/2, that's going to determine the height. First time I plug in 0 into the function, that's going to determine the height of this rectangle. The height of this rectangle is when I plug 1/2 into the function. The height of this rectangle is when I plug 1 into the function. So that's those values, and then we get that. So you can see from this picture, when you have an increasing function, the LRAM is going to be an underestimate. when you have an increasing function, the RAM is going to be an overestimate. And the MRAM is going to be just right in the middle. Same process, only here's my first rectangle. I go to the middle of it, I go up, and that's where I set the height. Here's my second rectangle. Go to the middle of it, go up, and that's where I set my height. So this is midpoint. MRAM, we call it. Rectangle area measurement. Midpoint rectangle area measurement. Left rectangle area measurement. And then you can see this one is kind of somewhere in the middle of an overestimate and an underestimate. So when you have an increasing function, increasing f of x, the underestimate will be your LRAM. So the area you get using your LRAM will be the smallest one. Midpoint, or MRAM, will be in the middle. And your RRAM will be an overestimate, so that'll be the largest area you get. Okay, so I just think that's a nice picture. The hardest part about this is drawing these darn rectangles. So here's just another picture of an increasing function of what these all look like. LRAM, MRAM, RRAM. Okay, now this one is where we get to practice a little bit of drawing. So I think I will demonstrate, I don't know, I'll do LRAM here. And then I think I'm going to ask you to try RRAM here. Just practice drawing them. That's the best way to do this. And then MRAM. So let's say we're going to do 5 rectangles here. Okay, and you'll do the same thing, 5 rectangles. So if this is 0 to 10, so I'd have 10 minus 0 divided by 5, this is going to say how wide my rectangles are. So my rectangles are going to be 2 wide. So once again, that delta x is width of your rectangle. Probably could have figured that out because this goes from 0 to 10. So the width of the rectangles are 2, so that's going to be my first one, second one, third one, fourth one, fifth one. So this is exactly how you're going to start. You're going to draw kind of the bottoms of the rectangles that are 2 wide. Okay, so now for LRAM, this is my first rectangle, I'm going to go to the left side, go up until I hit the graph, and then this is going to be the height of my first rectangle. So there's my LRAM. Okay, there's my second rectangle. Go to the left side of it, go up till you hit the graph, and then that's the height of your rectangle. So that's got to go all the way over to 4. So there is my second rectangle. Third rectangle, the base of it is right here. Go to the left, go up till you hit the graph, and then that sets the height of that third rectangle. So that goes all the way over to 6. Okay, fourth rectangle, left side, up till I hit the graph. That's the height of my rectangle, over to 8. Okay, last rectangle, left side up till I hit the graph. This is strange. These last two are very close to the same height. Now practice these two, RRAM and MRAM. And then maybe we'll look briefly at those in class. Okay, Mrs. Myers did this example in her video. So let's look at this one. This is actually a homework problem, page 270, number 2. A particle starts at x equals 0 and moves along the x-axis with that velocity function, 2t plus 1, for for time greater than 0. Where is the particle at time 4? So this is asking where. So that means distance. Oops. And that is going to be area under the curve. Okay? So it's traveling at this velocity, which would be distance over time, right? So we would have, I don't know, I'm just going to say meters per second. And then if I multiply that by time, seconds, the seconds will cancel and I'll end up with just a distance. Okay? So I need to graph this first. So this is a line. This graph is really small, but I'll do my best here. There's 1 and a slope of 2. Y-intercept of 1, slope of 2. So up 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So it's kind of a straight line. And then I have to do until time equals 4. So when t equals 4, v of 4 would be 2 times 4 plus 1, so that would be 9. So over 1, 2, 3, 4, up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's that point right there. So this is the area under the curve that I am looking for. Okay? So now the first thing you might be thinking is, I can find this area under this curve by simply, this is a geometric shape. I can do that. And actually that is fine. I think we do that in 5.1, where we use the geometric shapes to find the area under the curve. Now you could also do the rectangle, the LRAM, RRAM, or MRAM to estimate. But I'm thinking we have a nice geometric shape here. And if I divide this, you could do an area of a trapezoid, but sometimes I find it's easier to say, well, I have a triangle here and a rectangle here. So the area of this triangle is going to be 1/2 the base, which is 4, times the height, which is, I'll be careful, it's not 9, it's actually 9 minus 1, so that would be 8. So that's going to be the area of that triangle, and the area of this rectangle is a base of 4 and a height of 1. So the area under curve is going to be, this would be, 1/2 of 4 is 2, 2 times 8 is 16, plus 4, so that's going to be 20. So remember, this function right here, which is velocity, is in meters per second, or these units I made up. So that's my height, and then I'm multiplying that by my base, which would just be seconds. So the seconds would cancel, and this would be meters. So that would be the distance that this traveled. Where is the particle at time equals 4? So it traveled 20 meters. Ooh, but we better check v of 0. V of 0 is 2 times 0 plus 1. So this is how far it traveled. And it started at 1. So where is it? Particle is at 19. Okay, so that is it for 5.1, the two videos together.